Greetings, welcome to chapter 6. We're going to be talking about inference for categorical data in this chapter. So to start off with, we're going to do a quick recap of everything you just finished reading because of course you've read the section prior to getting to this, and of course you watched all the course videos that gave you some information about this. So let's go take a look at it with respect to the textbook. We're going to kind of this is a good spot if you haven't put all the stuff in your reference book already to get it out, and let's get that stuff in there to help you out with the rest of this activity or this lab, okay? So we're first going to look at inference for a single proportion. When we're working with categorical data, what we're going to be doing is basically using the binomial distribution, and what that means is we're going to be counting the number of successes, and we're going to see how many successes we got out of the entire sample. Okay, so we define a new sample statistic that we're going to use quite earnestly here, and that's called p hat. And what p hat is that's the sample proportion, and it's defined to be x over n, where x is the number of successes, our good old friend from the binomial distribution. Didn't change, okay? And n here, well, that again is from the binomial distribution. That was the number of Bernoulli trials. So that's how many trials we took, okay? Or the count of how many you actually did. And so the proportion of that's given by p hat is an estimate of the proportion of successes we would see in the entire population. So we're going to start off with inference for a single proportion. Well, how would we do that? Well, as it turns out, the binomial distribution is really well modeled by the normal distribution, provided that the sample size is large enough. So we will know that we can get a normal distribution, or a very close to being normal distribution. In other words, we can get a distribution that looks not quite unlike but similar to this of our p hats, provided that certain criteria are met. Okay, well, what are those criteria? We'll talk about those down here. We say, well, then you got to have, first of all, independence of observations. And basically what that means is you need to have a simple random sample. I mean, we've been talking about that pretty much throughout the course, is that your observations need to be randomly collected, and they need to be independent of each other, which means you can't take too much of the population and assume independence. So that, typically speaking, for the things we're going to be doing with this technique is not an issue, provided that you're random. But there's another criteria here, and it says you're going to have 10 successes and 10 failures. And what that means is that n times p has to be greater than or equal to 10, and then n times 1 minus p, excuse me here, I make a quick little correction here, 1 minus p being the probability of failure, that also has to be greater than or equal to 10. And the reason for that is that we will lose this bell-shaped curve if we don't have that. All right, if we have the situation where your proportion, your p, is really close to 0 or really close to 1, and your sample size is not very big. So in other words, if p is close to 0 and your sample size is small, then the shape of the distribution of your sample proportions, this is a hat here by the way, p hat, the shape of those sample proportions is going to end up being skewed to the right, because what's going to happen is that your mean that you're trying to estimate of the true population proportion is going to be over here someplace. On the other hand, if your true population proportion, if that's somewhere close to 1, in other words, if it's approaching 1, then what's going to happen is that the shape of your distribution is going to be skewed to the left, because the mean of the p hats is going to be someplace over to here. Now, these two shapes happen when your n times p is not greater than or equal to 10, and your n times 1 minus p is also, again, not greater than or equal to 10. But if you have met, this is the success failure criteria, if you meet the success failure criteria, then the distribution of p hats will be approximately normally distributed, with its center being at p, the true population proportion, and the standard error will be given by the probability of success times the probability of failure divided by the sample size, all of that square root of, okay? This we'll just call a math miracle for the moment. If you're interested in the mathematics where that came from, let me know and I'd be happy to explain that to you. Okay, so that's important stuff. So when we go to use the techniques that we're going to be developing in this chapter, we always need to check the success failure criteria and make sure that indeed the sample size was large enough to be able to use the normal approximation. Okay, so let's go take a look at what we just said, kind of in recap. All right, so we make sure we know how this applies to when we're talking about a confidence interval and how this applies when we're doing a hypothesis test. Because notice this chapter is about inference for categorical data, which means confidence intervals and hypothesis tests. Okay, so that both of these, in both cases, you need to have the success failure criteria needs to be met, and that means that there needs to be 10 expected successes and failures. Again, that means that n times p is greater than or equal to 10, and both has to be true, and that n times 1 minus p, the probability of failure, that also has to be greater than or equal to 10. Okay, so when you're calculating the standard error for a confidence interval, we're going to use the sample proportion to do that. In other words, the standard error for confidence intervals will be calculated just as the standard error was for when we were working with means. We ended up using S instead of sigma. We had to use the estimated value. So same idea here. When we're working with confidence intervals, we will calculate our standard error using our estimated values. On the other hand, as we did when we were working with hypothesis tests for means, if we're going to be working with a hypothesis test, there will be a null value. There'll be a value given by the null hypotheses, and we'll use that value of the null hypotheses in our calculation of the standard error. So that's a little bit tricky. You got to keep that in mind. It more or less is self-correcting. It'll make sense as you're doing it, that you know that the standard error of in a hypothesis test is always the null value.